In a previous video in our vector analysis series, we had proven Stokes' theorem. Now, in this video, we want to prove the Divergence theorem. Hopefully, we have an intuitive approach here that will make sense. It'll take a while to kind of put all the pieces together, but let's just follow it and see if, again, if this is worthwhile. Let's start off with what is the flux of a vector. And that basic concept is pretty straightforward. Suppose that this is an area element of magnitude A, and here is a unit normal vector to that area surface. So the unit normal vector times the magnitude of the area, that would be the area vector. And again, it's perpendicular to that surface of area. Then imagine that we have a vector here, f, and we want to find its components along the area vector. And of course, the way we would do that is just take the dot product. And that's what's called the flux. So it's a pretty straightforward concept. If instead of having a regular area element, if for example we have a differential with sides dx and dy, we can still have a normal vector to it. So then we would have a normal differential vector that is perpendicular to this surface. And imagine again we have some vector f, and we want to find its components along the differential area vector. And of course, we would do that just by taking the dot product. Now let's think of this in a little bit more detail. Suppose that we have a differential volume element in the form of a cube. And we have sides, this is a side dx, dy, dz, and right in the middle of the cube we have a vector, a three-dimensional vector. So of course it will have components f1 times the unit vector I plus f2 plus f3. And we want to know what is the differential flux of this vector for this differential volume element. And we would obtain that then by finding the differential flux for each one of these 6 faces and then adding that together. So, for example, here at the right-hand face, we'd be taking the dot product of the vector with the differential area A1. And this is just dA, and that vector would just be the j unit vector. So what we're calling dA1, this vector, would just simply be dA1 times the j unit vector. And we'll have this written out more explicitly in just a few moments. What we're trying to show here is that before we take that dot product with the vector f and this differential area vector for the right-hand side here, we first have to move the vector from the middle of the cube where it's sitting over to where it's in juxtaposition with this right-hand face. So that means we're moving at a distance of dy over 2. Well, with most of our problems, we're in a vector field, so that each f1 and f2 and f3 components of the vector can be a function of the x, y, and z variables. This, of course, is just a hypothetical here for these specific values, but the point is that when we move the vector from here over to here, we're moving it in a y direction, so that would change then the y components of the vector. So when we move the vector from here over in juxtaposition with the right-hand face to take the dot product to in turn get the differential flux for this face, we're going to change the value of the vector when we move it from here to here, and we'll deal with that in just a few moments. In fact, let's look at this problem only in more detail now. So here's our differential cube. And we have sides dx, dy, dz. The unit vectors I, j, and k. And let's say now that we want to find the differential flux for the right-hand face, and we'll do it for the left-hand face too, and add those together. So we want to consider the vector f. Then for the right-hand face, take this dot product. And then for the left-hand face, take this dot product. And add them together, and that will be the flux for the left-hand face and the right-hand face. So let's consider this. What is an DAR? As we'll see, that's just dx dz times the unit vector j. Dx dz and the unit vector j would be perpendicular to that face. Over here, of course, it's just going to be dx dz times minus j. We always want the vectors, the normal vector, pointing away from the surface. So here then, of course, the vector f, we just express that in general form. Like this. And we want to take the dot product of that with this. And this is dx dz j. So we take this dot product, and that will just be j dot j f2 dx dz. However, we have to think now. To take this dot product, we first had to move the vector from the middle of the cube a distance of dy over 2, so to be in juxtaposition with that right-hand face. So that means that, as we just showed, since each of the components are a function of x, y, and z, and we just shifted it in the y direction, then this was originally in the middle of the cube, but now we have it at the right-hand face. So it's going to change. So what we're trying to say here is that this, the f2 component of our vector, when it's in juxtaposition at the right-hand face, what will that equal? Will be what it was originally when the vector was sitting in the middle of the cube, plus this expression. Let's just go back up to the cube for a moment. So when we were in the middle, when the vector is sitting in the middle of the cube, it of course has these three different components. Now we shift it over to here, so each one of these is going to change. That, and that, because each one of these is a function of x, y, and z, and we just changed the y position of the vector. The x and the z's, of course, stayed constant as we just moved it along this horizontal line, a distance of dy over 2. Of course, we're interested now in, after taking this from the dot product, we're interested in just the F2 component. So it's going to be what it was originally when the vector was sitting right here, plus the amount of change when we shifted the position. And how much change is that? It's the partial of F2 with respect to y. That tells us how the F2 component changes with respect to the variable y, times the amount of change in the variable y. So this is equal to this. That's our value for F2 at the right-hand face. So we have F2 plus the partial of F2 with respect to y dy over 2 times dx dz. And this is the flux at the right-hand face. So remember this expression. We'll use this in just a few moments, but let's now determine what the flux is at the left-hand face. So I guess we'll have to make some room to do that. Now we want to know and dAl. And of course that, as we just shown, is just minus dx dzj. So we have a minus sign here. And of course we're going to take that dot product, F dot and dAl. And again, taking the dot product, that's 0, so we have minus F2 dx dz. But now this is the value, remember, of the second component when the vector has been shifted over to the left-hand face. Because now we shifted it from here over to here, and then taken that dot product. Now when we shift it like that, these two of course change. We don't care about that because when we take their dot product, these are 0. So we're interested only in the F2 component, how that changes. So now we have the component, the second component of our vector, when it's shifted over to the left-hand face, that will equal what it was originally when the vector was sitting in the middle of the cube. Now we shifted a distance of minus dy over 2. So that's the component, or that's the second component of our vector when we shift it over in juxtaposition at the left-hand face. We were here. When we go to the right, that's a positive distance. Go to the left, that's a negative distance of dy over 2. So this equals minus f over 2, or f of 2, minus the partial of f of 2 with respect to y, dy over 2 times dx dz. and this is the flux at the left, or the differential flux at the left differential face of our cube over here. And again, let's just go over this one more time because this is crucial, this step right here. And we're taking the dot product of our vector with this, but after we move the vector from here a distance of minus dy over 2. When we do that, because each one of these is a function of x, y, and z, each one of these components, we move the vector over to here, we've changed the vector then. But we're interested only in the F2 component, because these will be 0 when we take the dot product. So how does F2 change? It'll be what it was originally. Now I've gone a distance of minus dy over 2, but this partial derivative, this tells us how f of 2 changes with respect to the variable y times the amount of change of the variable y. That will be how much the F2 component changes when we shift position from here over to here. So that's that right there then. This is the component of the vector when the vector is in juxtaposition at that left-hand face. So this is then the differential flux at the left-hand face of the vector. So now let's add it up, this and for the right-hand differential. So we have, remember what it was here, for the right-hand differential, that was equal to, we'll get rid of this, that was f of 2 plus the partial of f with respect to y dy over 2 times dx dz. So if we add this and this together, f of 2 minus f of 2, that's 0. Then we have this minus negative this. So we have this plus this. That will give us the partial of f of 2 with respect to y dy. When we add these two together, then we have times dx dz. So this then is the total flux for the left-hand and right-hand faces, differential faces, added together. And if we go through this same process, not just for the left and the right-hand faces, but for the front face and the back face and the top face and the bottom face, nothing different, it's just doing the same thing only in different directions, then we get very similar expressions. For the bottom face plus the front differential face, the differential then, the differential flux is this, and then for the, this is the back face, this is the front face, this is the bottom face, and this is the top face, and that total differential flux is this expression. So the total differential flux for our cube will be these pairs added together, the left and the right differential face, the bottom and the back, and this should be an f for the front, plus the bottom and the top, or that's this, what we just showed in detail here, plus this and this. Similar expressions, and again, we're not going to derive these in detail because we're doing exactly what we did before here. We're just doing it in different directions. When we add all these together, we will have this plus this plus this times dx dy dz, which of course is just a volume element, dv. So for our cube, the total differential flux is this. Now, to appreciate the significance of this, we have to back up a step and remember the del operator. This is the expression for the del operator. Here's our vector f. If we take the dot product with these two, take the dot product of our del operator with the vector f, that will just be then the partial of f1 with respect to x plus the partial of f2 with respect to y plus the partial of f3 with respect to z. And the dot product of the del operator with the vector that gives this expression, this is called the divergence of the vector. But now you can see this is exactly what we had right here. So now we have, for our cube, the total differential flux is equal to this expression. So we're almost at the end here. Let's make some room on the whiteboard and kind of tie these concepts together, hopefully in a way that will make sense now. We know that the total flux, remember now we're just considering a differential volume element. The total flux, of course, that will be the integral of this. But now remember what dψ is. This is f dot n dA. But as we also saw, this is also this. We just derived that. So this is also the divergence of the vector times the differential volume element. So now, when we consider integrating this, for here, this will be a surface integral. So we have psi, which of course is equal to the total flux, which is equal to this, will equal, here it will be a surface integral. F dot n dA, but here will be a volume integral. Of the divergence of our vector f. But of course, and this right here, this is the divergence theorem. So hopefully that kind of gives an intuitive insight as to why this surface integral is equal to this volume integral. And again, that's the essential concept that's involved with the divergence theorem. Okay, this video is going to be a little bit long. We're going to wrap it up right now then, but hopefully that did provide some insights to this relationship. The playlist for all the videos here in our vector analysis series you can find at the website digital-university.org.